Now we have the layer of the sun that divides the inside of the sun from the atmosphere layers of the sun. This is a layer of the sun called the photosphere because when you take a photograph of the sun, this is what you see in your photograph, is this portion of the sun. So you think of that like it's the surface of the sun. It's a surface, but not the kind of surface that you could stand on because the sun is still all just made of gas. So we're not seeing anything solid here. We're just seeing as far down into the sun as we can, and you can't see anything below this level because the gases are too dense below the photosphere. The photosphere also shows us that the temperature dropped. Like we've been expecting, the temperature drops as you move away from the core. And this temperature is down to 5,800 Kelvin for the surface of the sun. That's a number close to 6,000 Kelvin. If you can remember 5,800 or remember 6,000, that's good. That would be helpful in the future if we need to refer to this. Because when people talk about the temperature of a star, they are usually talking about the temperature that shines out from the surface of the sun. So for our star, we would say the temperature of our sun is 5,800 Kelvin. We're not talking about the temperature of the core or any of the other layers, just the temperature of this brightest outer layer that we see shining out towards us. As we go now through the different features of the photosphere, we're going to see something called granulation. We're going to see vibrations on the surface of the sun, and of course we're also going to talk about sunspots. Now this is a photograph that does a nice job of showing a sunspot, but that's not what I want you to look at in this photograph. I want you to look at this part of the photograph where you see lots and lots and lots of little white areas which have dark edges around them, and they're all crowded together. When people looked at photographs like this and saw this was what the surface of the sun looks like, they said it looks like the surface of the sun is covered with grains. So that's why it's called granulation. And these granules, these white areas, are not small, 1,000 kilometers wide. That's bigger than a typical state in the United States. So why are they all grainy and bunched together like that? What is that showing us when we see granulation on the surface of the sun? What we're really seeing is the result of the convection that is coming up from just below the surface of the sun where you have the convection layer. The convection tells us that the hot gases are going to rise up towards the surface. Well, they're hot, so they're going to glow really bright and make a nice bright center. But then they release some of their heat and they cool off. So the cooler gases roll off towards the edges, and then that makes a dark edge around the granules, and that's the portion of the gas that is receding and going back down under the surface to catch some more heat and come up again. So this is a process that is like looking at the top of boiling water. You would expect to see with boiling water, you're always going to get hot gases rising up and releasing as steam, and then the water goes back down to get boiled again when it's cooled off and has to go down and seek the heat source. So this granulation, this boiling on the surface of the sun is happening all the time because of the heat of the sun. It is the result of convection. If we were in our actual classroom setting, I would escape out of the PowerPoint now and I would show you these two videos. This video on the left would be actual time-lapse photography of granulation on the surface of the sun. And if I ran this, you would see as the clock rolls around in the time-lapse photography, the whole surface of the sun is just churning and boiling. Instead of just looking at a static picture, all of these little white centers disappear and are replaced by others that come up from below the surface. So the surface of the sun is all moving around all the time because of this boiling. Over here, this video would show you somebody did a good job of doing a computer simulation of granulation to show us that when we know the laws of physics and how things work with thermodynamics and heat and gases, we can do a calculation that would tell us the hot gases would rise up, they would cool, and then the cooler gases would sink back down. And running this simulation would show you The darker portions, as they sink back down below the surface, and then the hotter portions that rise up will form these white patches up here. And this surface would change just the same way that you would see the actual granulation changing over here. Sorry, I'm not going to show that to you now. We're going to move on. What are we looking at here? This cannot be a photograph of the surface of the sun. We've never seen the sun like that. And I want you to get used to that in this series of lectures on the sun, because you're going to see other photographs where it doesn't look like a regular photo of the surface of the sun. When you see that, you should be able to answer the question, well then, what kind of photograph is that? Is that showing me the sun in a different wavelength of light, or is it showing something else? In this particular case, we're talking about the vibrations on the surface of the sun, and what we're doing in order to show you that the surface of the sun vibrates is we're showing you a map of where the surface of the sun has portions that are moving away from you at the same time that the one next to it is moving out towards you. So remember your Doppler effect that we talked about before. Red Doppler effect means redshift, and that portion is moving away from you. So this patch is moving in towards the core of the sun, at the same time that blue shift means something is moving out towards you. So this portion moves out away from the surface of the sun. So as we go across the surface of the sun, and we've used Doppler effect in order to map this out, we see that the surface of the sun has portions that move away and towards and away and towards and away and towards. And once it's moved away from you, it reverses and moves back out towards you. And the other ones reverse also. So these portions are going up and down and up and down and up and down on the surface of the sun all the time. Those are vibrations. And they're not small. They're huge. 200,000 kilometer wide patches. This is the result of pressure waves in the sun. Because we have all of these gases under pressure trying to rise up towards the surface, it creates this situation where there are resonant vibrations coming up from the sun, and it just echoes back and forth inside the entire volume of the sun. So remember, if you see a photograph like this, you are seeing something which is a mapped out Doppler effect, not just a regular photograph of the surface of the sun, and that shows that the surface vibrates. Here's what you really expect to see on the surface of the sun. Sunspots. Sunspots are not small. 2,500 kilometers is a small sunspot. 50,000 kilometers is a big sunspot. Back in March of 2001, there was this very large grouping of sunspots, which was 14 times the size of the Earth. So sunspots are huge. And when we look at them on the surface of the sun, sunspots are also dark. But what does it mean to be dark on the surface of the sun? Remember the granulation? The dark edges are the cooler parts. The white parts are the hotter parts. So a large dark patch on the sun means you have a large cool patch on the sun. How can anything be cool on the surface of the sun? But actually, if you were to take the temperature of these patches of the sun, where the darkest portion is called the umbra, and the portion around the sunspot is called the penumbra, and then you get up to the regular granulation on the surface of the sun, the umbra is really 4,300 Kelvin. That's still hot. I still wouldn't want to touch that. So it's relatively cooler than the 5,800 degree temperature of the surface of the sun. And then the penumbra is a temperature of around 5,000 Kelvin. So the temperature works its way up as you go back up to the surface. If you were to block out the surface and take a photograph of these inner hot layers, then they would shine out bright. But in contrast to something else that's hotter and brighter, they look darker by comparison. So that's what's happening when you're seeing dark sunspots.